welcome to another module in this massive open online course. So, we are looking at the Lloyd Max quantization algorithm for the design of the optimal quantizer, and we have said that the Lloyd Max quantization algorithm, we compute the quantization intervals, that is basically the boundaries of these quantization intervals and the corresponding levels or the quantization the levels in each quantization interval iteratively, alright. So, we have a set of quantization intervals which are characterized by the boundaries. So, these are your quantization intervals, that is you have your M0, M1 up to ML, these characterize the intervals, correct. And also we have your nu1, nu2, so on up to nu L, these characterize your levels, and we compute them iteratively. Okay. Compute iteratively. Iteratively as part of the Lloyd Max quantization algorithm. Okay. So, that is what we are doing. Now, let us start with computation of the quantization levels, alright. So, let us start by illustrating how to compute the quantization level nu k corresponding to the quantization interval m k minus 1 m k, that is given the quantization interval m k minus 1 to m k, what is the corresponding optimal quantization level nu k, right, to which sample will be, to which the sample will be quantized to if it lies in this particular interval. Okay. So, let us consider quantization interval. So, consider this quantization interval. Consider this interval. Now, we would like to ask the question, what is the optimal or what is the best quantization level corresponding to this interval? What is the best quantization level corresponding to this interval? Okay. What is the best quantization level corresponding to this interval? Okay. Let that quantization level be denoted by nu k, all right. Let the level be denoted by nu k. Let the quantization level be denoted by nu k. Okay. Now, how do we choose this optimal quantization level nu k? Obviously, we are interested in the lowest quantization error, that is we are interested in minimizing the power or the variance of the quantization error. So, we should choose the quantization level nu k in such a way that is it minimizes the quantization error, but quantization error is a random quantity, therefore, we should choose it in such a way that it minimizes the variance of the quantization error. Okay. So, choose nu k such that, so basically choose nu k such that average right, average quantization error, average square of quantization error, let us put it that way, square of quantization error is, average square of quantization error is minimized. And further notice that we are choosing the square of the quantization error, not just the quantization error. We are not simply minimizing quantization error. The reason for this is as follows: you can have a high quantization error, and if it is both positive and negative with equal value, equal probability, then the average quantization error will still be 0, right. So, even so if you minimize simply the average quantization error, it is not guaranteed to minimize the absolute value of the quantization error, alright. To make sure that not just that the quantization error on an average goes to 0, but the magnitude of the quantization error is also small, we minimize the square of the quantization error rather than simply the quantization error. And we know that we are given that FMM, now for this we know that Fm of M, we know that this is the probability density function of the sample. Okay. Now, therefore, now what is the quantization, now what is the square of, now quantization error is basically nu k, if the sample is m, quantization error is nu k minus m, nu k minus m square is the square of the quantization error. Now, I have to weigh it by the probability density function and integrate it in this interval. Now, what is my average? I will integrate it now to compute the average over this interval m k minus 1 to m k. I have to integrate it between the limits m k minus 1 to m k, and now this gives me the average quantization error corresponding to threshold nu k in the interval m k minus 1 to m k. Now, let us write this is your average quantization error for the interval m k corresponding to the level nu k. And what we would like to do, we would like to find nu k which basically minimizes this, alright. So, find nu k which minimizes this quantization error or which minimizes the average quantization error, alright. Now, find nu k find nu k which minimizes the average quantization error, alright. So, now we have the average, we have the means, this is also known as the mean squared, right, the average value of the square of the quantization error, the mean square quantization error corresponding to that interval m k minus 1 to m k, alright, in the interval m k minus 1 to m k corresponding to that particular threshold nu k. Now, I have to minimize this with respect to nu k, therefore, naturally I can differentiate this with respect to nu k, set it equal to 0, that will give me the value of nu k for which the quantization error or the mean square quantization error is minimum. Okay. So, therefore, now to find the minimum, I simply differentiate this quantity with respect to nu k, m k minus 1 to m k, nu k minus, well, m whole square f of m dm. Remember, I am using the probability density function to compute the average. Now, take the derivative inside. Now, this is equal to, well, integral m k minus 1 to m k dou partial with respect to nu k minus m whole square, well, f of m. Now, observe that this only this portion nu k minus m whole square depends on nu k, and the derivative with respect to that is fairly straightforward. This is m k minus 1 to m k dou the derivative of nu k minus m whole square is twice nu k minus m, that is it, f of m dm. Now, what we have to do is we have to equate this to 0 and this is equal to 0, this we are doing to find nu k for which square error or mean squared error find error for which mean squared error is minimized. Okay. And therefore, this equating to 0 is only for the purpose of that. Now, we get an equation. So, now of course, we can cancel the 2. So, the equation that we have is m k minus 1 to m k twice nu k minus m f of m dm equal to 0. Now, this implies if we solve this equation, this implies, well, of course, the 2 cancels, m k minus 1 to m k, well, nu k f of m dm, this is equal to integral m k minus 1 to m k, well, f of m dm. Now, nu k is a constant. Okay. Now, observe that nu k is not a constant, it does not depend on m. So, it can come outside. So, this does not depend on m. Nu k, it does not depend on the sample value m. Okay. So, the integral is with respect to m, therefore, nu k is a constant with respect to m. So, it can come out of the integral, okay, and that will lead to the simplification. This implies, now you see something interesting, this implies nu k integral m k minus 1 to m k f of m dm is equal to m k minus 1 to m k m f of m dm. And now, we have an elegant expression for nu k, and this implies, well, nu k equals integral m k minus 1 to m k m f of m dm divided by m k minus 1 to m k f of m dm. Okay. And this is basically this is basically the optimal value of the therefore, this is now the optimal value for this is the optimal value nu k for the interval m k minus 1 to m k, which minimizes. Optimal in what sense? Optimal in the sense that it minimizes the mean squared quantization error. All right. Optimal in the sense that minimizes the mean square quantization error. Okay. You can see that optimal in the sense that minimizes and you can see this formula, if you look at it, which gives optimal quantization level nu k, if you look at it, it is simply integral m k minus 1 to m k m f of m, that is weighing average of the probability density function in that interval divided by the total mass, that is mk minus 1, the total probability mass, right, integral mk minus 1, right, integral mk minus 1 to mk f of m dm, basically it is the probability density function in integrated between mk minus 1 to mk, which characterizes the total probability that the sample lies in that interval. From a physics perspective, you can think of it as the, if the probability density function corresponds to a distribution of mass, you can think of it as the total mass, right, characterized in that, the probability mass that is characterized in the interval. And the numerator integral mk minus 1 to mk m fm dm, that gives the location, right, that is basically location of the average, right, average of the distribution of the mass. Therefore, the average divided by the total mass, that gives the location of the center of gravity, right, in a physics perspective. This were to give a mass distribution, this is similar to a physical interpretation in terms of the, so this quantization level basically is similar to the center of gravity corresponding to that interval mk minus 1 to mk, if fm if this probability density function fm of m can be thought of as a probability, as a distribution of mass of an object. Okay. So, you can see that analog, this is nothing but the center of gravity if it is basically the center of gravity, you can think of it as analog, as an analog from physics, you can think of it as a center of gravity corresponding to that interval. Now, this also you can show that corresponds to the conditional mean, alright, we know what is the mean of the probability density function. Okay. The mean of a probability density function is again simply minus infinity to infinity this is the mean. Okay. Now, this expression nu k, that is integral mk minus 1 to mk m fm dm divided by integral mk minus 1 to mk fm dm, this corresponds to the conditional mean of the signal sample that is conditioned on the signal sample belonging to this interval mk minus 1 to mk, alright. One can also note that. So, this also corresponds to conditional mean. This also corresponds to the conditional mean of the signal sample, be conditioned on the fact that the signal conditioned on the event that the signal sample belongs to this interval mk minus 1 time. So, you can think of it that this is basically your expected value of m conditioned on the fact that m belongs to mk minus 1 comma mk. This is what, this is your nu k. This is the conditional mean conditioned on the fact, conditioned on the event that m, the signal sample, lies in this quantization interval mk minus 1. Alright. So, that gives us a nice elegant expression to compute the optimal quantization level nu k corresponding to this quantization interval mk minus 1 to mk. Now, we have the other problem, that is, given the quantization levels nu 0, nu 1, that is nu 1, nu 2 up to nu l, how to compute the quantization intervals m1, m0, m1 up to ml. Okay. So, now let us look at the other problem, that is, now let us look at the other problem. Okay. Now, let us find optimal, well, the other problem m0, m1 up to ml given nu 0, nu 1 up to, or nu 1, nu 2 up to nu L. Okay. Now, in this M0 and ML, which are the first and last points, first and last boundaries, we can ignore them because M0 ML basically are determined based on the dynamic range of the quantizer. So, these we can ignore. So, the first and start ignore as M0 ML are determined from the dynamic range. These are determined from the dynamic range, alright. So, these we are going to ignore, okay, because these are fixed for a particular quantizer, as we said the initial and the final values, that is the total interval of quantizer, the total interval of quantization is determined by the, or the total range of the quantizer is determined based on the dynamic range of the signal, and that has to be chosen appropriately, okay. So, this we are going to leave. So, we are going to focus on how to determine the intermediate boundaries, that is we are given this total interval over which the signal can lie, which the signal sample can lie, alright. The signal sample can belong can lie in this interval M0 to ML, this is known as the dynamic range of the quantizer. We are going to determine where to place these intermediate boundaries, that is M1, M2 up to ML minus 1. So, how to choose, it is really how to choose M1, M2 up to So, we are really asking the question how to choose M1, M2 up to ML minus 1. And now, that is basically, let us consider this scenario, that is let us consider again the same scenario Mk minus 1 to Mk. So, now the scenario is different, we are given, well we are given nu k, we are given nu k plus 1, okay, alright, and we are going to choose how to determine Mk, okay. So, we know that nu k is the quantization level corresponding to Mk minus 1 to Mk. So, given Mk, so given nu k plus 1, how to choose Mk? How to choose Mk, okay. And this can be done as follows. Remember, we want to choose Mk. Now, Mk has this property, if x is greater than Mk. Now, Mk is the quantization, now Mk minus 1 to Mk is the quantization interval, okay. So, if x lies to the right of Mk, it is quantized to nu k plus 1. If x lies to the left of Mk, it is quantized to nu k, okay. So, let us note that property. So, if lies in this, okay, this region quantized to nu k plus 1, while this region, that is if the sample M lies in this region, if the sample M lies in this region, this is quantized to nu k, okay. So, therefore, we have to choose the this threshold, right, we have to choose this the threshold in between this nu k and nu k plus 1 such that the quantization error is minimized. Now, if now let us look at this for, and now let us look at this, correct. If q of x equal to, okay, if let us consider any point x, let us consider any point x, okay, let us consider any point x, or consider any sample x, consider any sample m. Okay. Now, if m is quantized to nu k plus 1, that is if q of m equals nu k plus 1, then error or square error equals, well, square error equals x minus nu k plus 1 square. Similarly, if q of m equal to nu k, on the other hand, if q of m is equal to nu k, the square error is nu k minus x whole square. That is, if x or I am sorry, let us put this as m. Okay. If q of m is quantized to nu k plus 1, okay, then the error is m minus nu k plus 1 whole square. On the other hand, if it is quantized to nu k, then the error is m minus nu k whole square. That is the simple fact. Now, we have to choose nu k or nu k plus 1, alright, whichever minimizes the square of the quantization error. Therefore, we choose nu k, that is, we choose nu k, that is, choose nu k, therefore, choose nu k only if m minus nu k whole square is less than or equal to, well, nu k minus m or n minus nu k whole square, it is the same thing, m minus nu k plus 1 whole square. Okay. That is the important observation, that is, you are choosing nu k only if the square of the error m minus nu k square is less than or equal to m minus nu k plus 1 square, that is the square of the error, quantization error corresponding to choosing nu k plus 1. And now simplifying this, this implies and is implied by m square plus nu k square minus 2 m nu k less than or equal to m square plus nu k plus 1 square minus 2 m nu k plus 1, which implies and is implied by, of course, the m squares go away, which implies and is implied by, well, 2 m nu k plus 1 minus nu k less than or equal to nu k plus 1 square minus nu k square, which is again implied and implied by, note that nu k plus 1 minus nu k is positive, 2 m less than or equal to nu k plus 1 square minus nu k square divided by nu k plus 1 minus nu k. You can verify that this is simply nu k plus 1 plus nu k, which is basically implied and is implied by m less than or equal to half, which is basically implies and is implied by m is less than or equal to half nu k plus 1 plus nu k. And remember, this is choose nu k. So, choose nu k if choose nu k if m less than or equal to half nu k plus 1 plus nu k. Okay. So, that is the whole point, that is, we choose nu k if m is less than or equal to half nu k plus 1 plus nu k, and therefore, automatically the threshold becomes, that is m k, alright, automatically the threshold becomes m k, which is half nu k plus 1 nu k plus 1. Okay. So, if m is lying to the left of this threshold, you are choosing, well, nu k. If m is lying to the right of this threshold, you are choosing nu k plus 1, and therefore, the threshold, that is m k, the threshold is nothing but m k, that is the boundary of that interval, the boundary of that interval is half nu k plus 1 plus nu k. Therefore, now, therefore, this summarizes, therefore, the threshold or basically boundary of interval is, well, mk equals half nu k plus nu k plus 1. Alright. So, now given these quantization levels, you can find the optimal boundaries of the quantization intervals. For instance, m1 equals half nu 1 plus nu 2, m2 equals half nu 2 plus nu 3, so on and so forth. ml minus 1 equals half nu l or nu l minus 1 plus nu l. Okay. These determine m1, m2 up to l minus 1. So, these determine your m1, m2, ml minus 1. We said that m0 and ml, we are going to determine them from the dynamic range of the signal. So, we are not worried about them. We are determining the intermediate thresholds corresponding to the various intervals. So, m0 to m1, that is one interval, m1 to m2, that is the next interval, so on and so forth, ml minus 1 to ml, that is the last interval. Okay. Now, from the quantization levels, we have determined the intervals. Now, again from the intervals, one can go back and determine the optimal quantization levels nu 1, nu 2, nu l, that is step 1. Okay. So, this is step 2, alright. If you remember, this is basically your step 2. Okay. If you go all the way back and look at our Lloyd Max quantizer design, you will recall that basically the Lloyd Max, I am sorry, this is step B, alright. Step A is to determine the given the quantization intervals, determines the levels, that is what we have done earlier, alright. The levels can be determined as the center of gravity of each interval, treating the probability density function of the sample m as the mass, as the distribution of the mass. Okay. That is step A. Now, step B is basically given the quantization levels, determine the intervals, and we have determined the level simply as the midpoint of each nu k plus 1, that is half of nu k plus nu k plus nu k plus 1 is nothing but the midpoint between nu k and nu k plus 1, that determines the boundary m k, alright. So, that is step B. Compute step A and step B iteratively, okay, that gives the optimal quantizer. Okay. So, we have basically this is your step B. Now, compute step A, step B iteratively. Multiple iterations, this yields the optimal quantizer, this yields the optimal Lloyd Max quantizer. This yields the optimal Lloyd Max quantizer. Again, optimal in what sense? Optimal in the sense that it minimizes the mean square minimizes the mean squared quantization error. So, that is what we are getting. Okay. So, compute step A and step B iteratively, that yields the optimal Lloyd Max quantizer. which minimizes the mean squared quantization error. That gives us how to determine the optimal quantizer. Remember previously we had only seen a very simplified version of the quantizer, that is a uniform quantizer, which need not, which is a very simple, which is simple to implement, but obviously need not be optimal in the sense that the quantization error might still be very large. So, the Lloyd max algorithm gives an iterative, a convenient iterative algorithm to determine the optimal quantizer in the sense that the quantization intervals and the quantization levels which minimize the mean squared quantization error. Alright. So, we will stop this module, stop here and look at other aspects in subsequent modules. Thank you very much.